Welcome to Capacitors, everyone. Teaching of capacitors for both the algebra and calculus students is everything you gotta know. Let's get started.
So a capacitor relies on electrostatics for its operation, okay? So a capacitor is often drawn as two parallel plates, and those plates are separated from each other. The two plates are conducting plates, but they are not connected to each other, so they cannot conduct between them. Rather, one plate is connected to one side of a battery, while the other plate is connected to the other side of the battery. There are specific symbols that I should be drawing to represent the battery, but we're going to cover that in the circuits unit. Let's say this is the positive side of the battery, this is the negative side of the battery. Let's say this is a 5-volt battery. What does that mean? How is the capacitor going to work? Okay. What happens is, first of all, charges, positive charges, are going to drift out from this end. Now remember the technicality here. Positive charges don't actually move. When I say positive charges drift this way, what's actually happening is negative charges are drifting in the opposite direction. Just keep that technicality in mind. And on the right side of the battery, negative charges are going to be flowing in this direction. Okay? Therefore, the left side, the left plate, is going to become positively charged. And the right side, the right plate, is going to become negatively charged. So, I have positive charges and I have negative charges. Therefore, within the capacitor, there is a net electric field going from positive to negative. Okay? The positive charges are also exerting an electrostatic force onto the negative charges. So they are pulling each other together. Okay? So I can build up some charge on here. I can build up some charge Q on the capacitor, and then I can remove the battery from the circuit. Okay? At that point, when I remove the battery of the circuit, the charges can't go anywhere. The charges stay on the capacitor. Okay? Which means I have some amount of charge Q that is stored in the capacitor. There is some electric field between those two ends, and they are stored at some potential difference. Okay? Let's reanalyze what the potential difference means in this case. Potential difference, delta V, is often denoted as electromotive force. Now, electromotive force, the symbol is the capital epsilon, okay? So there's a reason for that. Electromotive force is interpreted in circuits, in capacitors, that is the force with which charges move through the circuit. So if we reconsider the fact when the battery is connected to the capacitor, positive charges are flowing to the positive plate, but as positive charges accumulate on the positive plate, they repel more positive charges, which means every positive charge that comes on is going to be harder to put onto that plate than the previous one, because the more positively charged the plate is, the more it will repel additional positive charges, and the same is true for the negative plate, okay? So that means that charge will continue to flow from the battery onto the capacitor until the voltage potential difference across the capacitor is equal to the voltage potential difference across the battery. Okay? We discussed previously that voltage always flows from charge always flows from high potential to low potential, meaning that at the beginning, our capacitor is charged with 0 volts because it has 0 charge, but as charge begins to accumulate on the capacitor, it develops an electric potential of its own, and it will continue to increase its electric potential until the potential is exactly balanced between the battery and the capacitor. And since electric potential is balanced, no current will flow. No charge will flow from one capacitor to the battery or from the battery to the capacitor. The equation on your reference table that describes this relationship is C, the capacitance of your capacitor, is equal to the charge it can hold divided by the potential difference applied to it. Okay, so what does that mean? If I were to take this battery out and replace it with a 9-volt battery, The 9-volt battery, being a higher potential now, would force a great deal more charge onto the capacitor. Okay? So a capacitor doesn't have a set constant capacity, rather it has a set constant capacity for a given potential difference applied across it. Means if I am only gently pushing charge into the capacitor, then it can only hold this much. But if I apply more electromotive force, if I apply a greater potential difference, then it can hold a great deal more. Okay? And that ratio between the charge the capacitor can hold divided by the potential difference, the electromotive force that you need to apply to it, is the capacitance. And the capacitance is a constant. It's like the mass of an object. It doesn't change. Another equation that we have to describe capacitance is C equals kappa epsilon naught area over distance. So what specifically does this mean? Kappa is something we're going to discuss in just a few moments. We're going to keep that in the back of our heads right now. So let's only consider this section of the equation. Okay? Epsilon naught is a constant. It's the vacuum permittivity constant. So I want to rewrite this equation as the capacitance is proportional to the area over the distance. So in a parallel plate capacitor, again, these are plates. So if I turned this circuit 90 degrees and I looked at it from a different angle, this would look like a square to me, or some plate. Okay? So therefore, the capacitance is equal to the overlapping area. What do I mean by overlapping area? In the two plates, it's very common for you to have two plates that are the exact same size and shape, but in the off chance that you don't, in the off chance that you're given one plate that is bigger and one plate that is smaller, like a circle, the area in this equation is a reference to the overlapping area between the two plates. So in this case, the overlapping area would just be this pi r squared, the area of the circular plate. Okay? The distance is the separation, the distance between the two plates. Okay, so what does this equation tell us? It means that the larger the plate, the larger the capacitance. The larger the plate, the more charge the capacitor can store, which makes absolute sense. If I have more space, I can put more stuff there. The distance, as distance increases, the capacitance decreases. As the separation between the two plates increases, the amount of charge I can store on the plates decreases. Why is that? Because as distance increases, recall that I said there was an electric field from positive to negative here, okay? One of the main contributing factors to the point that the positive and negative charge can stay on this plate is because the positive charges are attracting the negative charges and vice versa, okay? It's because the electric field. If I separate the plates a greater distance, I would decrease the value of the electric field. If I decrease the electric field, these two charges feel less of an attraction to one another. So they're not going to want to stay on that plate, okay? So that's the contribution of distance. Next equation we have is our potential energy stored in a capacitor, given by 1/2 times Q times the potential difference, which is analogous to our electric potential energy equation, which is just a charge Q times its potential, okay? But we're focusing on this right now. We can rewrite this equation in a different form, say with this equation. We can say that our potential difference is equal to Q over C. So therefore this can be rewritten as 1/2 Q squared over C, or we can do Q and say that Q equals C delta V. So the potential energy stored in a capacitor can again be rewritten as 1/2 C delta V squared. So it's important to understand how you might be able to rewrite this equation in terms of what you're given in your problem. We're going to discuss the conservation of energy applications of this equation next unit in the circuits unit, probably my favorite unit. But until then, it's just important to understand this equation, okay? From there, we move on to the concept of dielectrics, which is the kappa, the Greek K that I told you not to worry about in this equation. Well, now we're going to worry about it, okay? What is a dielectric? A dielectric is a non-conducting material that I put in between my parallel plates, okay? In the dielectric, the negative charge on the right plate is going to attract positive charges inside the dielectric. So positive charges are going to become present on this side of the dielectric. On the positive side, of course, is going to attract negative charges on the dielectric. Therefore, we can see here that the electric field created by the negative plate is satisfied by the electric field by the positive charges in the dielectric, okay? So the polarization of the dielectric acts to oppose the electric field created by the plates, okay? So if the electric field created by the plates goes from positive to negative, the electric field inside the dielectric also goes from positive to negative. They oppose each other, okay? If I have a negative charge is really unhappy when it's alone. Negative charge wants to be as close as possible to positive charge, and the dielectric constant helps it do that. Therefore, any dielectric will increase the capacitance of your capacitor. It makes the charges on each plate more stable. So therefore, more charges can be accommodated on any given plate. So that is why your dielectric constant is in the numerator of your capacitance equation. The higher the dielectric constant, the more polarizable your dielectric. The more polarizable it is, the greater its ability to mitigate the repulsive forces, the greater its ability to keep the negative and positive charges happy, keep them stable, okay? So the dielectric constant, kappa, as you might assume, is a constant. It's a constant that's characteristic of the material. I can't remember if I mentioned, but I'll just say it again. The dielectric is an insulator. It's not a conductor. If it were a conductor, then negative charge would just flow to positive charge. It's an insulator. The equation of the dielectric constant, kappa, equals epsilon over epsilon naught. Now, this requires an understanding of what exactly epsilon naught is, okay? Epsilon naught is vacuum permittivity, is the permittivity of free space. So what does that mean? It means permittivity is how easy or how much electric field can permeate a material, okay? So the permittivity of free space is basically saying how much electric field is free to permeate or free to move throughout a vacuum, okay? So E naught is vacuum permittivity, and E is going to be the permittivity of our dielectric, okay? It's a measure of how polarizable, how easy electric field can move and stabilize through the material, okay? So in the context of that, the dielectric constant makes sense in terms of its application. Okay.